Okay, so I've got my directory full of NICMOS images. I've opened a terminal. I run out of T-shell instead of bash, but you guys can figure that out. I'm going to cd over to my directory. So I'm going to run everything out of the directory with the files. That'll make things just easier to navigate. So there we are. Let's make sure we're there. Okay, and so I'm going to start IDL, and then I'm going to start IDP3. Okay, so now we have IDP3 running. This is what you should see. I've set it up so that the parameter files should specify the GUI for laptops. Uh, you can fix all that by going into Edit Preferences, which will let you set all kinds of things, and I've already got it set up the way I like it. You can set it up the way you want to, and when you save this, it will save your preferences. Unfortunately, it won't save them for the next time. You have to do that separately, either with a preference file that's in the working folder or with the master preference file that's in the IDL IDP3 directory. I'm not going to show you that in this particular video. This should work for everybody at least to get going. And if we need to tune it for later, then we will. So once you have IDP3 running, move this up here so it's not out in the way. What we want to do is load up some images. There's a couple ways to do it. You can load them one at a time, or you can load them in blocks, just like a Mac. So you hold down Shift. I'm going to go ahead and load up everything because I know I'm going to need them all. So I will highlight them all and hit OK, and they've all loaded up over here. This is my primary display control window, and over on the left you can see the images now. They're all 8 there. So 4 of them are the object, which turns out to be a hyperluminous infrared galaxy, which is basically a quasar that's obscured with some other stuff around it, maybe. We're going to find out. And a point source. And I will point out that we have designed this just like we will do most JWST observations for chronography. This isn't chronography, but it's the same principle. We will always try to get a star that's brighter than the target so that we don't have to integrate as long, and yet we get the same signal to noise. As you know, this may cause some problems with the background, especially for myriad long wavelengths, but we can fix that. All right, so one of the first things we want to do is to be able to see down into the noise. So we're going to adjust the display, which is right here. And for now, it's on auto and it's linear, which is good. It shows you most of the things, but I'm just going to click square root. Well, let's click log first, and you can see there's some garbage left over from the NICMOS processing. We're not going to worry too much about that right now. Let's use square root instead. And you can see that over here, there's the footprint of NICMOS. It's a 512 by 512 array. And so we don't want to see all this black stuff. So what we can do is we can draw a region of interest, which should sound familiar to all of you who have been around me and the OCD for a while. And this will bring up this neat thing, this region of interest. And the cool thing about this is there's lots of tools here. You can blow this up. So let's go ahead and do it by a factor of 2. If you have a bigger screen, you can even go a factor of 8 or 4. The important thing to realize, though, is that I am not in any way doing anything to the original images at all, ever. So this is a non-destructive process unless you overwrite images on purpose. This is non-destructive. It loads everything into memory. So it is memory. It's a memory hog. Uses a lot of memory, but nowadays with 16 gigabytes on a laptop, you should be fine. And if you need more, well, we'll work on that. All right, so now there's my region of interest. I have my objects. I can turn them all off over here. Just hit the off and hit redisplay, and they are gone. I can hit on, and they will all pop back on. Right now, I'm going to turn them all off, except for my primary object. There it is. You can already see that there's some fluff around this. It's not just a regular point source. I'll turn that off and then turn on a point source, which is right there. And you can see it's a little different. So there's the NICMOS point source, and this is a target. And so what we're going to do with IDP3 is we're going to do a couple things. The first is we're going to just make some astrometric measurements. And the simplest way to do that is we will turn on this image. Notice this is on. There is a star here, and the star is important. The star will tell you what image is the reference image. And what I mean by that is whenever you manipulate images, one of the images is going to carry the main header that will be written to the final product. And so you want to make sure that you've clicked that image and there's a star by it before you save anything. Now you can do all kinds of things. I can make that the reference, this one, whatever. But in the end, the header that I want written to the file, which will have all the correct information, including astrometry, has to be the one that's got the star by it. So be careful with that. And when we get further in the video, you'll see how that works. All right, so the other things you can do real quick is I can turn these two on and then I can subtract them even though I haven't moved anything yet. So go over to subtract, and obviously they're not lined up, so that's not working very well. I can multiply take a minimum of the two. I can invert one of them. I can divide by one. I can do multiply. I can do all kinds of fun stuff. But mostly what we're going to do is either do subtractions, or for the astrometry and the exercise today, we will be primarily using add because we want to see what's going on. All right, so let's turn off the object and let's just concentrate on the point source. We want to measure the position of the point source, both in detector space, which is down here, X and Y, and also we're going to want to measure RA and DEC, which is up here. All right, so what we're going to do is in the region of interest, now remember we're in the region of interest, not the primary display. We've blown up this area. Let me just show you that you can also do it this way and make a smaller region if that's what you want. I'm going to stick in the larger space so I can see everything as I'm moving. All right, so there we go. Okay, so come up here. I want a radial profile. I can do a crosscut. Just to show you that quickly, I can do a crosscut if I want, and it'll pop up a crosscut. That's not what I want right now, so I'm going to close that. Instead, what I want is a radial profile. So I'm going to center this roughly, doesn't have to be exact, on this point source and draw out past at least the first set of area rings. And there you go. It's a little crude. I can actually improve that a bit by going to 4. Now it's a little smoother, but it's harder to see on this small screen. And mathematically, it doesn't matter. So we're going to have to do two things. We're going to do a weighted moment fit and a Gaussian fit. But we have to first give that program a guess, right? Otherwise, it'll wander off and maybe not find the proper fit. So we'll do a quick full width half maximum. Then we'll hit the centroid. And that was hard to see, so let me zoom this down a little bit. All right, just do it again. I always do it twice to make sure these numbers change just a little bit as you refine the fit, but it converges usually within 2 passes. All right, so now we have a very good estimate of the center of this object, at least on the detector. And these are the detector coordinates. You've got the moment and the Gaussian. They're very, very close. This gives you the difference between the two. If you care, it'll give you a measurement of the full width half maximum in both X and Y, which is a little bit different than this for reasons that I will go into in a different discussion. But also up here you've got you can figure out the centered coordinates. So now what we want to do, all right, there's some things you can look at in here. You can do a Gauss show. This will show you the object, the raw data, fitted data, which you can't see really. And then this is the residuals, both in a contour and in a image, and you can plot the image in underneath it. And you can save the fit and the residuals if you want, and also the raw image. But we're not going to do that right now. Instead, we're going to save this information so we can print it, which will make a picture in PostScript or TIFF, but we're going to save the centroid or the radial profile. We can save the centroid in a file. So this is PSF1 centroid.txt, and we will save it, and as I'll show in a little bit, yes, they're all on that I care about. You can also do, I could fit all of these things, and then any of them that are on, it will save into the file. But we're just going to do one at a time. All right, so there's the first one. I'm now going to turn on the second one, but leave the first one starred, so it's the reference. I'm going to turn off the second one, and I'm just going to do the same procedure for each one. And you'll see in a minute why I'm doing that. So do that, get an estimate of this full with that maximum, do the fit, estimate, fit. Now you can see it's converged. All right. Then I'm going to do the next one, turn that off, turn this on. You can see there's some goopy stuff on Nick Moss that we're trying to dither around. So there's that. Like I said, it doesn't have to be that precise. Just click that, 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 and that. Now you have a centroid, and again, here's your coordinates that you could write down or you could save to a file. And then we'll turn this one on. Notice it's over here in space, so these are picking up those bad pixels. So we'll just do another circle over here, and we'll click that, and we'll click that. Do 2 fits. This PSF, I don't know what's wrong with it. I never get a good fit on this one, but the centroid's fine. All right, so I've done all 4 of them, and now I have the data, and I've either written it to file or I've written it in my notebook. Other reason I did this with all 4 is because the other thing you can do with this is turn all 4 of these on. And because we did centroids, and because number 4 here is starred, I can do something really fun, which will align all of these objects based on the centroid in detector coordinates without regard to the RA and deck. And so I can do that right here. And I say align by centroids. And there they go. And they're all aligned. And you can do some tests to see how good you did. So we can turn 2 of them off and then subtract the second one from the first, and it's not bad. NICMOS has some issues because it's on HST and the HST breathes. We should not see this with JWST. If we do, well, then we'll know there's an issue. Okay, so I'm going to turn them all back on. Now I've got a series of 4 images aligned, and I know what the coordinates are. They are going to inherit the world coordinates from this image. So if I go up here, I can read off the world coordinates up here of my cursor, and those will be the correct coordinates for everything that's been shifted. So they're all in the proper tangent space. All right, but that's all well and good. The whole purpose of the dither was to make an image that is median filtered, basically, to get rid of the garbage. And so I can go up here, and I can combine images right here. I'm going fast, but here's combine images. And I can combine them with a median. I can combine with the mean, sigma clip mean, sigma clip median. In this case, I'm going to use a sigma clipped median with plus or minus 3 sigma because I know there's a couple of artifacts in NICMOS that can cause problems. I'm going to save the results into IDP3, so there'll be another image that pops up here, but I'm also going to save it to a file, and this is going to be called, let's do this, F160W, so we know what filter we're working on, median, whoops, sig clip median dot fits. If you don't put an extension on the end, it will save it as dot fit, F-I-T. And that's historical because it goes back to the days when you couldn't have 4 letters on a descriptor. All right, so we do that. Now we don't hit done yet. We still have to compute the median. So we hit compute. Something happened. That something is right here. You can see it took those images and row by row, it did medians of all the pixels and made you a final image. And that final image is over here. So now I've got the 4 images that I had that made the median, and they're still full of garbage, right? Bad pixels and other things. So if I turn those off, I'm just going to hit this and turn everything off, and then just turn on the median one. It's nice and clean in the area of overlap. All right, so there we go. Now let me show you something else that you can do with IDP3 that will also be handy and will allow us to test the world coordinate transfers. Now remember, this was all done in pixel space. So now I'm going to show you how to do things based on world coordinates. So I click here. Now this is going to be my reference, and it's my quasar, my hyperluminous galaxy. And remember, there's 4 of them. So I'm going to turn them all on. Again, this is the reference image, though. This one, whoops. This one right here. And in this case, they're all on, and they're all going to be referenced to this. And here, I'm going to align them by world coordinates. Align by world coordinates. And if all the world coordinates are correct, then we should get the same result as doing it by hand with the detector coordinates. So here we go, boom, and there it is. And there they all are. Let's do a couple checks to see how well it aligned. Let's turn these 2 off. Let's subtract this one. And it's pretty good. Again, the residual here in the PSF has to do with telescope breathing, and there's not much we can do about it. That's why we developed a library called Laplace for chronography, because we have breathing effects. And in this case, it's not chronography, but we still see the effect. So I'm going to turn these back on. And just like I did last time, I'm going to stack these. I'm going to median stack them. So I'm going to combine them with a sigma clip median, and this time I'm going to call it by its name, IRAS 23060 plus 0505. All right, that's its telephone number. And again, I have to remember to press the compute, and then it does its job. It loaded the median image here, and I'm going to click done to get rid of that. Okay, so I'm going to turn everybody off, and then I'm going to just turn on the quasar, the hyperthermal galaxy. You can see we later figured out how to dither properly so we can get rid of this bad column, but that's a different story. And we can turn on our PSF. Now, those are not aligned, and they should not be because they were taken at slightly different offsets in celestial coordinates. In the next video, we'll continue with the process of PSF subtraction.